All right, here we are, last part 5, the final installment of Module 4. So for this module here, we're looking at optimization problems. Optimization, to optimize something means to maximize or minimize some part of it. In businesses, you may want to maximize profit or minimize cost. This is where a lot of the economic applications come into play, which some of you were talking about in the discussion boards. In shipping, you may want to maximize volume of a container while minimizing its surface area. The majority of optimization problems will be given two equations, one to optimize and the other one will be a constraint of some form. All right, and you have to be creative with your substitution. All right, I'll show you what that looks like when we go through these examples. So with Boxes Inc., they want to design a box that has a square base and a surface area of 108 square inches. What dimensions will produce a box with a maximum volume? All right, so we want the largest volume, but while trying to maintain a certain amount of surface area. All right, so I'll do what I normally do, and that's start off by drawing a picture. So here's our box. All right, so it has a square base. I'm going to call that x by x, and it has an unknown height, and there's no top. So that's there. So the volume of this box is x squared times h. Side times side times side, length times width times height. All right, the surface area would be x squared plus 4xh. All right, because you've got the square surface, the bottom, that's x squared, right? There's no top, so we don't have to worry about that. But then this is x by h, and we have 1, 2, 3, 4 sides that go around those sides. And so we know 108 will equal x squared plus 4xh. All right. So here are two equations, what we're trying to optimize and what our constraints are. Okay. You could do this where you differentiate both of them, swap out dHdt's, and figure everything else out that way. There's actually a much simpler way. If this is all in terms of x, we can just take the derivative of it in a normal fashion. All right, so that would require solving this for h, and this is what I was talking about with being creative with substitution. Whatever your constraint equation is, you're going to want to plug that into whatever it is you're trying to optimize. All right, so if we simplify this, we're going to get 108 minus x squared all over 4x equals h. All right, so for the purposes, volume equals x squared times 108 minus x squared all over 4x. Volume equals 108x minus x to the third over 4. This guy and one of these cancel out, distribute the x, you're good to go. So there's our volume. And this is nice because now you have volume expressed solely in terms of x, so when it comes back to find out what the actual volume is, makes life a little bit easier. So v prime is 108 minus 3x squared all over 4. No, we do not need the quotient rule because it's just a constant of 4 in the denominator. Up here we would have needed product and quotient rule and all that other fun stuff, but we can avoid that because we simplified. A little algebra goes a long way. Set this equal to 0. And when you set it equal to 0, you get x to equal -6 and +6. However, we're just going to use 6, all right, because the -6 really doesn't make much sense because You can't have a negative dimension. So that only gives us x. So we know our box is going to be a 6 by 6 by something, right? So we want to find the height. Well, it turns out we have a formula for height right here. So if we do at x equals 6, 108 minus 6 squared over 4 times 6 equals h equals 3. So the box should be 6 by 6 by 3 inches. So those are your box dimensions. What would the volume be? The volume would be, volume equals 108 cubic inches. That's fun. Okay, so like we did with the related rates video, you can pause here, try the next one on your own, and then see how you do, or just keep on watching me do the problems and save the work for when you are doing your homework. So what's the area of the largest rectangle that can be inscribed in the parabola y equals 16 minus x squared if the rectangle must be entirely above the x-axis? What? So let's draw a picture. So here's my parabola. And inside of here, I'm going to draw my rectangle. Okay. And for the record, I know this is -4, this is +4, and up here is 16. So I have to get a number between 4 and 16 for my x and y values. Okay. So this is the point x comma y, right? So if this is xy, that means we can now figure out the dimensions of our rectangle. Our rectangle has a height of y and a width of 2x, because that's x, right? They're both x away. Because remember, we're measuring distances. So we end up with 2x. So our area is 2xy. And we want to maximize area, so we need to take the derivative of this. But we have a constraint. So we'll substitute that in. Area equals 2x times 16 minus x squared, which I'll simplify further. 32 minus 2x cubed. So a prime would be 32 minus 6x squared. 0 equals 32 minus 6x squared. It just dawned on me, in none of the other videos, I don't think I ever explained why I was setting these equal to 0. Setting these equal to 0 is because we're looking for a maximum or a minimum. We would also look at where it's undefined if that was applicable as well. So, yeah, turning points, critical points occur at x equals 0. That's the first two videos we did. So we do this, x squared would equal 32 over 6, which means x would equal radical 32 over 6, which would equal 4 over the square root of 3. So x, yes, that's our value for x, which is the same thing as 2.309. So what's the largest area available to us? Largest area. Well, we know area is 32x minus 2x cubed. So that's our area formula from right here. So I'm just going to plug 4 divided by the square root of 3 in. So we have 32x minus 2x to the third. So the area would be 49.267 square units. So that's an optimization problem. So just to recap an optimization problem, you're going to have a couple of equations. You're going to have two. One of them will be your what you're trying to optimize. The other one will be the constraints. You have to do some creative substitution between the two of them to make them work. And then once they're substituted, you should be good to go. Where is it? So that concludes this module. All right. Hopefully you found it informative. Just to recap everything we did here. We solved for extrema using the first and second derivative tests, and we did curve sketching. These were your first two videos. Then we talked about the mean value theorem. Mean value theorem says the instantaneous rate of change equals, there has to be some point where the instantaneous rate of change equals the average rate of change. And remember, your function has to be continuous on the closed and differentiable on the open. If that hypothesis is not met, you cannot apply the mean value theorem. Then we talked about related rates, which are one of my personal favorites and boatloads of fun. And then the optimization problems as well, which have started to grow on me. I wasn't a huge fan of those when I first started teaching the course, but now that I've been doing it for a while, I find them more fun and interesting to do. I saved going over the first and second derivative tests on purpose, because remember, your derivative tells you your rate of change, right? Your instantaneous rate of change. And for a function, your rate of change is constantly changing. It's dynamic, which is why we need derivatives. If derivatives and slopes were constant, then everything would be static and it would be extremely boring. So if your derivative is positive, you're increasing. If your derivative is negative, you're decreasing. And whenever you have a sign change or the derivative does not exist, that's when you're in a position where you have a possible maximum or a minimum extrema. Second derivative is all about concavity, whether you're concave up or concave down. And points of inflection are where you have a sign change and your second derivative is equal to 0. Okay, so I'll be in office hours if anybody has any questions on any of this. Be more than happy to help you. So thanks, and hope to talk to you soon.